way we have done for heat and fluid flow problems, we first tried to build our concepts based on a shell balance. But we have seen before as well that using a shell balance is extremely useful for clarifying our concepts. But when the problem becomes slightly more complicated, especially in terms of geometry, then it would be difficult to imagine or to visualize such a shell and identify all the terms contributing to heat or momentum transfer. So, we have used the same approach for mass transfer as well. So, we started with a shell balance. It is a species balance across a shell of some small thickness, which we made almost tending to 0, and got our differential equation. From the difference equation we got the differential equation, and that differential equation can then be integrated with proper boundary conditions to arrive at the concentration profile. So, if you would like to generalize such a system, can there be an equation which we will be able to use without resorting to that that shell balance approach? This is what we are going to do today. Now, we are going to do species balance. So, if it is species balance, so it should be somewhat similar to mass balance, because what we are doing is nothing but mass balance considering one species and taking into account all the different mechanisms by which that species can come into the control volume. Now, we are going to restrict ourselves to binary systems for this course, and also we are going to add certain other simplifications. This we have not discussed before, and we will probably not go into the details of that, but you can have mass. So far we have seen that mass gets transferred from one point to another by diffusion mechanism, and the diffusion is solely due to concentration difference between the 2 points. But there are other mechanisms, though not as prominent as concentration difference, by which mass can also get transferred. One of it is very interesting, which is due to surface tension gradient. Okay. If you have in a system surface tensions different at 2 different points, and what can be the primary cause for surface tension difference? And what is surface tension a strong function of? Temperature. So, if in a system you have temperature gradient, then that temperature gradient can in turn result in surface tension gradient, and this surface tension gradient in some cases can give rise to flow, to movement of one species from one point to another. So, this temperature imposed diffusion process, with the root cause of which is surface tension gradient, can also be substantial or can also be of importance in some mass transfer applications. A very common example is and surface tension is also a function of concentration. So, if you have a concentration gradient, not only you are going to have diffusion, you are also going to have surface tension gradient, which can in turn induce a flow from one point to another. Now, you know that the major thrust of materials processing today is to make a perfect crystal, to make a crystal from a molten mass of one component which is perfectly pure. So, for crystal growths and all experiments involving crystal growth, when a crystal grows, the concentrations are going to be different at different points inside the molten mass. And since crystal growth results in change in temperature, release or absorption of energy, so that would give rise to the temperature gradient. So, for all crystal growth experiments, there is absolutely no concentration gradient between 2 points. There may not be any concentration gradient. It is one concentration which is very high, and you add some nucleation sites and the crystals start to grow. So, when such a crystal grows, the temperature difference may induce a surface tension gradient, which would cause more liquid to come towards the growing crystal. So, this results in a specific type of flow which we will not discuss in this course, but you should know about it. It's surface tension gradient driven flow. This is known as Marangoni flow. Okay. So, some of you probably will be exposed to Marangoni flow later on in your professional life. So, these the root cause of diffusion, we are simplifying, we are oversimplifying probably if we say it's concentration gradient. It's not only concentration gradient, it's chemical potential gradient. A molecule of a species at a specific location, its chemical potential is going to depend on several things. Concentration is definitely one of them, but temperature and pressure can also give rise to a change in chemical potential. So, a flow, so diffusion takes place if there is a difference in chemical potential. So, all the factors which contribute to a change in chemical potential can in turn induce flow. So, you may have concentration equality, but temperature inequality. So, that will give rise to a flow. So, these are interesting effects and they are known as Soret effect, Lewis effect, Marangoni flow, etc. So, the analysis that we are going to do right now, we exclude those flows. We exclude the temperature dependent flow, the pressure diffusion, etc. It is solely based on concentration gradient driven flow. Now, when we are trying to deduce the equation of continuity for a binary mixture, it is nothing but equation of continuity, it is nothing but conservation of mass taking one species at a time. As before, we are going to assume a control volume which is fixed in space of dimension del x, del y and del z, and through each of these phases, x phase having area del y, del z, through x, y and z phase mass of species A, let us say component A, can come in as a result of diffusion, as a result of bulk flow. The species A may get produced inside the control volume or may get consumed inside the control volume by reacting with the second component B present in the mixture. So, there has to be a source term. So, due to this flow, diffusive and bulk, and something, let us say A is being generated in the system, due to generation of A inside the control volume, the concentration of A inside the control volume may change. So, when we are going to write the equation, we will identify the mass fluxes. In this part, we are going to refer mass flux as small n subscript component, that means small na refers to the mass flux of A coming into the control volume. We also emphasize at this point that Na can have two components, one is due to bulk flow, that is due to velocity, and second is due to diffusion, and we already know how to express capital Na, which is molar flux of A. So, we would like to formulate our equation based on all mass fluxes through the phases. So, NaX, what should it be multiplied with in order to find out the total amount? NaX is the flux of A in the which is coming through the X phase. So, obviously, the corresponding area which is del y del z, and similarly I am going to have for y component NAY multiplied by the area of the y phase coming at y, leaving at y plus delta y, same for z. The reaction is expressed in mass transfer as per unit volume. So, RA, if that is the reaction rate per unit volume, and when I use small r, that refers to mass produced per unit volume per unit time. If it is capital R, it is moles produced or consumed per unit time per unit volume. So, that small r A or capital R A must be multiplied by del x, del y, del z, volume of the total control volume, which makes it mass per unit time. And as a result of all these, the concentration of A inside the control volume will change with time. So, the change of concentration of A inside the control volume with time can be expressed as del rho A del T, that is change of concentration with time multiplied by, what should it be multiplied with? Everything else in that equation would be mass per unit time, all right. So, if del rho A del T, it is kg per meter cube per second, what it should be multiplied with then? Volume of the control, the whole thing. So, del rho A del T must be multiplied with del x del y del z. So, let us, without writing anything, let us think of the terms that we are going to have. Mass in at phase x, n A x multiplied by del y del z, everything evaluated at x. The one that leaves n A x, x plus delta x, and the area term. Through y phase n A y and n A y plus delta y multiplied with del x del z. Through the z phase, same thing, n A z multiplied by the proper area in minus out. Then I have the reaction term, which is going to be R A, reaction per unit volume, amount kg per unit volume multiplied by per unit time multiplied by the volume. And secondly, we are going to have the result of all these, the resultant of all these is change of concentration of A inside the control volume. So, the amount of mass of A accumulated inside the control volume as a function of time, which would simply be del rho A del T multiplied by del x del y del z. So, the next step is simple, you divide both sides by del x del y del z, taking the limit when all of them approach 0, and the result that you are going to have is del x of n A x plus del y of n A y plus z term plus R A is del rho A del T. Is that clear to all of you? It is just a species balance, the same way we have done for equation of continuity. So, I am writing the equation of continuity for species A inside an imaginary control volume del x del y del z fixed in space. So, it is a fixed in space, fixed coordinate system. So, this is nothing but equation of continuity for A. And rho refers to mass concentration, C refers to molar concentration. What we are doing is conservation of mass for species A inside a volume element del x del y del z fixed in space. So, this equation represents the change in mass concentration of A with respect to time at a fixed point in space as a result of fluxes of mass coming into the control volume, and we understand that this flux can be diffusive flux as well as bulk due to bulk flow, the result of and a contribution from generation or depletion of A inside such a system. So, if I would like to express this in a more compact vector form, then I would simply write del rho A del T plus divergence of the mass flux vector is equal to the reaction by which it is produced. Okay, it is nothing but a simplified form of this. So, if I can write this expression for this equation for A, I can similarly write the expression for B. So, change in mass concentration of B inside the control volume fixed in space is a result of mass flux of B into the control volume and the reaction rate with which B is being produced or destroyed. So, these two equations are going to be useful for us. What happens if we add them up? If we add this, let us think about the first term del T of rho A plus rho B. What is rho A plus rho B? Net concentration, net concentration of the system. So, we express it simply by rho. So, this becomes del rho del T. Okay. What is NA? I bring to your notice the equations that we have know, we already know, but I would like to reiterate one more time. This is the mass average velocity, the expression for which we have already seen. The star refers to molar average velocity. The density, I mean the mass density of the system is a sum of these two, whereas the mass density kg per meter cube is simply multiplying the molar density by molecular weight. This is the mass fraction, this is the mole fraction. The total molar concentration is a sum of the constituent molar concentrations, and the mass flux is rho A, mass flux of component A is rho A times V A. Similarly, it is defined that the molar flux is C A times V A, and N A plus N B, which is the total mass flux, is simply rho times the mass average velocity, whereas N A plus N B is the concentration times the molar average velocity. So, this is just to recapitulate what we have seen, what we have done so far. So, if I use such a methodology, then the sum of these two terms can simply be expressed by rho v. So, it is going to be del rho by del t plus divergence of rho v equals, what is going to be R A plus R B? We understand that N A plus N B is simply equal to rho v. What is R A plus R B? Any idea? What is the significance of R A? Mass of A produced. Mass of A produced. Significance of R B? Mass of B produced or destroyed? Consumed. Okay. So, it is a binary system. So, there is nothing else. So, to produce A, you have to consume B. Let us say it is B producing A. So, if we express it in mass terms, what is R A plus R B then? Now, think about it. It is going to be 0, since it is in mass terms, you conserve mass. So, for each kg of whatever, each kg of A produced, 1 kg of B has to be consumed. So, R A plus R B is going to be equal to 0. Just a quick question, if I express, forget about this equation, just these two terms, if I express these in terms of capital R A and capital R B, would R plus R B be equal to 0?
No.
May or may not be, do not say no with so much emphasis. If 1 mole of A is produced from 1 mole of B, then moles are conserved as well. So, moles may or may not be conserved, but mass will always be conserved. So, R A plus R B may or may not be equal to 0, but small r A plus small r B would obviously be always 0. So, if I come to this equation now, which is the conservation equation, and does this look familiar? What is this? It is equation of continuity for the whole mixture. So, it is consistent with what we have seen before in fluid mechanics, that if we consider the whole thing as one, then equation of continuity can be applied to this equation. And for a fluid of constant density, if its equation of, what is equation of continuity for a fluid of constant density? Grad of V is equal to 0. So, for a fluid of constant density, as you can see from this equation as well, divergence of grad of V would be equal to 0. So, so far we are consistent with whatever we have seen so far. Now, if I express everything in terms of molar fluxes, capital N A, molar concentration, capital C A, and the molar rate of reaction, which I am going to denote by capital R A, then the species continuity equation in terms of moles can be obtained using exactly similar approach as before. So, I am simply going to write the equation that I am going to get. Remember, everything in this is in terms of moles. So, R A will be moles per unit volume per unit time, and I can write the continuity equation, molar equation for species B as well, and if I sum them together, C A, realizing that C A plus C B is equal to C, is simply going to be divergence of C V star, as we have seen before, R A plus R B. Note that R A plus R B I may not be able to put equal to 0. So, if it is a case of constant density, the constant density, mass density here gave me divergence V equal to 0. This density, when I write as this density, this is molar density. So, if it is a constant molar density, what would be the form of this? It would be divergence V star is 1 by C of R A plus R B. So, this is the difference between these two equations when I express it in mass terms and when I express it in molar terms, and we can appreciate why the concept remaining same, why the form is slightly different. Okay. So, these are two special cases, but I am going to deal with this equation and the equation which I have, let us say I am going to deal with this equation, the component equation expressed in terms of moles, and similarly the component equation expressed in terms of mass, because without this I will not be able to use the full potential of this equation. I have to substitute N A in here and capital N A in here, unless and my ultimate aim is to obtain an expression for C A in terms of x, y, z and t. The other parameters would be R A, etcetera, D A B, etcetera. So, how do I replace capital N A or small n a? The same way we have done so far. Capital N A is simply going to be x A times N A plus N B minus D A B del C A del Z if it is just a function of Z. Similarly, small n A is going to be expressed in terms of mass terms. So, it is going to be in x A would be replaced by N A is equal to x A times N A plus N B and the second term. So, x A in that equation should be replaced by W A, where instead of mole fraction I am going to use mass fraction. Instead of capital N, which is in molar terms, I have to use small n. Rest of the thing will remain same. So, the two expressions that I would use maybe I will put it outside as this. So, these are the two equations which I should substitute. This I should substitute in the mass equation, this I should substitute in the molar equation. And if I do that, two completely equivalent equations of conservation of species A can be obtained. So, I am substituting this into my first equation, that is del rho A del T and all plus small n A, and I am substituting capital N A into this equation, which also I have obtained using similar approaches. So, once I do that, two completely equivalent general equations are obtained, which are del rho A del T So, these two equations are equivalent. One is expressed in mass terms, the other is expressed in molar terms. In one case the velocity used is mass average velocity, in other case the velocity used is molar average velocity. Apart from that, fundamentally there is no difference between these two equations. So, one can use either of these depending on the situation that we are going to deal with. The only restrictions on these two equations are the absence of any other diffusion mechanism that I have discussed before. So, there is no pressure diffusion, no thermal diffusion, etc. So, it's that is the only restriction we have on this system. Most of the times we are going to deal with this equation either using this as for the case where we are going to deal with mass concentration, or we can divide it by the molecular weight of species A, let us call it Ma, to convert it to molar concentrations. Why we do that? Because we generally find out what is the mass average velocity. We do not in general deal with molar average velocity. Mass velocities are easier to calculate, easier to measure. So, that is why this equation has more relevance in engineering calculations compared to the other equation which uses molar velocity. Okay. Apart from that, there is no difference. So, I am going to start with this equation and I will simply expand this term. So, it is going to be rho A times divergence V plus V times divergence rho A. That is going to be the only difference. So, I will deal with this equation and expand the second term on the right hand side, which would simply give me del rho A del T plus rho A divergence V plus V times divergence rho A is equal to dAB, taking the rho inside, divergence square rho A plus R A. So, if I use this, so this is the restriction that I have put in here is constant rho, constant rho and constant dAB. All right. If you compare it with the equation that I have written previously, if my rho is constant and dAB is constant, since rho is constant, I am taking it over here. So, rho times mass fraction is equal to rho A, and since dAB is constant, I am taking dAB outside and expanding this term, nothing else, which would give me dAB times divergence rho A. So, since it is a constant rho case, any simplification to this equation? Okay, so, this one is going to be equal to 0. No, this is, I said it is a constant mass density whole system, constant rho. I did not say anything about rho A. So, rho A may change with time, but since it is a constant rho system, divergence of V has to be equal to 0. So, if that is the case, del rho A del T plus V times divergence rho A is equal to dAB divergence square. This is the equation. Okay. Does this equation look familiar? Or maybe if I write it in terms of concentration, so if I have to write in this in terms of molar concentration, what do I have to do? Divide both sides by Ma, which is the molecular weight of A. What I would get is del Ca del T plus V divergence Ca is equal to dAB these would be two equations which we will use extensively. Okay. These two equations are going to be extremely useful for our analysis later on. So, let us look one more time and try to see how this equation, these two equations can be used, or what are the cases in which I can use these equations. Are they valid for transient cases? Transient cases where the concentration is a function of time as well. Definitely yes, I have a del rho A and del rho A, del T of rho A and del T of Ca. So, these equations are valid for transient cases. If it is steady state, only this part would be equal to 0. Okay. These equations can be used in mass terms or can be used in molar terms. What is del rho A del T plus divergence of rho A? Del rho A del T plus V into divergence of rho A. Can you think of any mathematical expression which would combine these two? D dt of rho A. So, and similarly for C A. So, this is substantial derivative. Okay. So, substantial derivative of this is equal to dAB times this dAB times divergence square rho A and so on. So, if that is the case, then the right hand side left hand side of this can also be written as dCA by dt is equal to dAB plus RA. Have you seen this equation before? This equation in some other form. I will write this equation one more time. dCA dt is equal to dAB Where have you seen this equation? It's not Navier-Stokes, no, it's not Navier-Stokes. Okay, let's try to convert this equation for temperature, I mean for heat, energy. Okay. What should dAB be replaced with? No, I am writing it for energy, K. What should CA be replaced with? Temperature. What should RA be replaced with? It is a heat generation or depletion term, basically a source term. So, let us call it a source term. Over here it should be d dt of T. Now, when we think of convective mass transfer, the energy contained, is it just T? T minus reference temperature or T minus reference temperature multiplied by something. How do I express the energy of a packet of fluid which is moving from one point to another? How much energy does it contain? We know that we have arrived at this by finding out how much mass is carried, rho times V, how much mass is carried from one point to another. That is how we got dCA dt. So, if that mass contains some amount of energy, how do you express that energy? T minus reference temperature or something else? It is T minus reference temperature. So, is it mass times T minus reference temperature or mass times something else as well? Specific heat, Cp. So, the mass can be m, but the energy contained is mCp delta T, where delta T is T minus reference temperature. So, in this case it would be rho times Cp times T minus the reference temperature. So, what should I have extra term over here? Rho times Cp. Okay. So, this is how, this is one example of analogous treatment between heat and mass transfer. We are going to deal with this approach later on in transport process 2. But even in here we can see that these two equations will form the basis for analogous treatment between heat and mass transfer. So, it is going to be rho Cp times dt, and you have used this equation many times in your heat transfer part of the course. So, this is a completely equivalent heat transfer form of this equation can be obtained by looking at, by simply replacing the terms which are going to come. So, a more common representation of this is, what is K by rho Cp? Alpha times T plus whatever, some constant 1 by rho Cp times S. So, you have used this equation. So, we'll use these two equations. One is important part, assumption of zero velocity. So, what is assumption of zero velocity without reaction? How do you, what would be the change in this equation? Let us say if I use the assumption of zero velocity and without any reaction, how do you simplify this equation? Without reaction, so obviously this is going to be 0, okay, plus 0. This one there would be no change, dAB divergence square CA. What is going to be the changes in d dt of CA? I said it is zero velocity assumption. Del CA, you are talking about this del, small del CA del T, and anything else? The rest of the terms are going to be 0 since your velocity is 0. So, you will have, if you assume 0 velocity and without any reaction, this is the form that you are going to have for diffusion. And if it is a steady state process, del CA del T would be 0. So, what you have is dAB, if it is a one dimension, let us say it is a one dimensional process, you are simply going to have d2 CA by dz square is equal to 0. Now, where do you think you can use this equation? What is the applicability of this equation? Where you have zero velocity? A diffusion, a case of diffusion where zero velocity can be assumed. Diffusion in solids, right, that is the case. This equation is applicable for diffusion in solids, okay, where you do not have, where something is diffusing through a solid, and this is the governing equation for such a case. This is also the governing equation. Have you seen this governing equation before in some of the problems that we have solved? I am sure we have seen it for the case of diffusion through diffusion and a homogeneous reaction in a stagnant liquid, where the X was small, the concentration of the species was small. So, if you look back at your class note, and you would see this is the equation which we have obtained, plus there was a reaction term, plus R A is equal to 0. So, whenever we are going to deal with solids, and in some special cases this would be the equation to deal with. And if I write the corresponding equation for heat, what is going to be here? You tell me what is the form for heat, energy. In Professor S's part of the course, you must have used this equation many times. Okay. So, and we ourselves have also derived this equation, and again this is the same as, fundamentally the same as before, where you can use these two equations for analogous treatment of heat and mass transfer. Now, in the time remaining, in about 5 minutes or so, I will introduce one problem which directly uses the one of this equation to solve a problem, and then we are going to have the tutorial. This is a conceptual problem. I have a salt layer which is exposed to water, okay, and the depth of the water is large. So, that means you have a level of water above the salt layer is quite large. Initially, the salt layer was separated from water, and at time t equal to 0, you remove that barrier between the salt and water. So, what happens? Salt will start dissolving in the water, and as it dissolves, the concentration of salt in the water very close to the salt surface will increase, and these will start to diffuse towards the top. So, as time passes, this layer, the top layer of salt, will progressively move in this direction, right. That's what's going to happen. You have to find out what is the recession rate of this layer. Recession rate of this layer. So, certain parameters are required, which is rho A s of the solid of the this thing is the solubility of salt in water is 380 kg per meter cube. The solid salt has a density equal to 2165 kg per meter cube, and DAB is given as 1.2 into 10 to the power minus 9 meter square per second. All right. So, the salt density is 2165, the solubility of salt in water is 380 kg per meter cube, and DAB is 1.29 into 10 to the power minus 9. This length, the thickness of the salt layer is L. What you have to find out is dl dt. Okay. What is the rate at which this L, thickness of the salt, is going to change with time, right. So, if I have to use any of these equations, let us see if I use this equation, what would be the form of this equation? Ra will be 0, there is no reaction between salt and water, and instead of dCA dt, capital D dt of Ca, what it is going to be? There is no velocity in the system, okay. It is small del T of Ca is equal to divergence square Ca. So, it is going to be, if I express it in mass terms, it is the same. This rho is in kg per meter cube. But there is no imposed velocity. You did not impose any velocity. That velocity, that extra velocity that you have is due to bulk flow. So, what we are assuming, you are right that why there is no velocity, because we have seen that rapidly diffusing solutes can produce a velocity in the system, as we have seen in some of the cases. In two cases, that would be equal to 0. One, if it is a case of diffusion in solids, which is not in this case, it is not a case of diffusion in solids. And secondly, if we assume that the concentration of the solute present in the liquid is not too high to introduce such a velocity. So, we are making an assumption, yes, that the velocity of the diffusing salt molecules in water, they are not going to create, they are not going to impose a velocity bulk flow in the water itself. So, the major case is, major assumption is it is a diffusion only case. So, if it is a diffusion only case, then only I can write this one. If it is a gas, obviously yes, you will not be able to make this assumption, but since it is a liquid, it is an assumption only. Now, how many boundary conditions do I need? How many conditions do I need to solve this equation? 3. One initial condition and 2 boundary conditions. All right. So, what is the initial condition that we are going to have? Initially, we had only water present in the system, because if you remember, like the salt was separated from the water by a barrier, and the barrier was removed at time t equal to 0. So, what is going to be the initial condition? Rho A at time t equal to at time t equal to 0 at any x, if this is my x, is equal to 0. What is the boundary conditions of the system? 1 and 2. That is, what can be the boundary condition? One is rho A at x equal to 0 for any time t is equal to, which one is this, 380 or 2165?
So I think it's solubility. So the solubility.
The solubility of the salt in water, because again my domain of this equation, validity of this equation is up to this much, not inside the solid. So, it should be equal to rho A S, that means it is going to be equal to 380. Second is what would be the other one?
Means our axis is getting changed.
X is slowly moving downwards, the coordinate is slowly moving downward, but we will have to do something else to find that out. My conceptually what I am trying to do is I am trying to find out what is the flux at this location x equal to 0. If I find the flux of salt at x equal to 0, that flux is going to be equal to the dissolution rate. Is that's the point on which the whole problem is resting upon. If we can find the flux of salt molecules at x equal to 0, that should be equal to the rate at which the solid salt layer is getting dissolved in water, and that would give us the recession rate. So, what is the other condition that I am going to find out? I am going to use? It is going to be another condition on x. So, obviously, this is going to be T, and what else can I say? I mentioned it is a deep body of water. So, this depth is large, infinity is equal to 0, all right. So, since you study much more mathematics in the other part of the course, I would simply ask you what is going to be the solution of this. One initial condition which is 0, the second initial condition which is defined at 0, x equal to 0 and x equal to infinity, and this is equal to 0 of this form. What would be the solution of it? Right. It would be much more simpler than that. I will not go into the solution. You know more about these solutions. You should know more about these solutions than me. It's simply going to be an error function solution. You have studied error function, definitely yes in the other part. So, I would simply write the error function solution of it. And what I would do, I would encourage you to do is, do not have to do the solution. For any number of PDEs, the solutions are already available. What you have to check is, you have done this case for heat transfer. Okay. You have a semi-infinite body which is at thermal equilibrium. Suddenly, you change the condition at one of the boundaries and find out how the temperature for front is progressing inside the solid. So, your initial condition is temperature is same everywhere. So, you have defined your temperature as T minus Ti, so as to make that new variable equal to 0 at time t equal to 0 at time t equal to 0. So, your initial condition was T equal to Ti for any x. So, you define a new variable theta which is equal to T minus Ti, such that theta is equal to 0 for all x's, and then at one boundary, that at x equal to 0, you have rho equal to rho As, that means T equal to Ts. At one boundary, it is equal to 0. At the other boundary, since it is semi infinite, that means at x equal to 0, your theta will be still equal to, theta is defined as T minus Ti. So, at the other boundary, what is for any t, what is going to be the value of theta? I will repeat it again. I will go a bit slowly. I have defined my theta as T minus Ti. Okay. Ti is the initial uniform temperature of the semi-infinite body. So, if theta is T minus Ti, then theta has to be 0, equal to 0 when small t is equal to 0. We have exposed one boundary of the semi-infinite medium to a constant temperature, capital T A, let us say. So, my theta becomes equal to theta A at x equal to 0 for all time. Agreed? So, that is clear. So, this is similar to what I have written here. Rho A is at time at x equal to 0 is a constant. So, your temperature, newly defined temperature is some theta s at x equal to 0. Theta is simply defined as T minus T I. Now, it is a semi infinite body. So, at the other end, when x tends to infinity, for any time theta has to be equal to 0, T is T I. So, can you see the similarity between a changed boundary condition, changed boundary temperature of a semi infinite solid and this problem? So, you have solved that problem of semi infinite solid where one boundary is suddenly brought to a new temperature, and you have seen, you will see if you just look at your class note from the other part, that the solution for that is error function. So, what I encourage you to do is look for similarities. Any problem in mass transfer, heat transfer, fluid mechanics, you need not have to solve all the problems to get all the problems. What you need to do is look at the governing equation, look at the boundary conditions. If they are the same, your solutions will also be the same. Only thing is you have to change DAB to K and something like that. So, the error function solution for that one is going to be substituted in here with the simple change of DAB to, I mean K to DAB, K by rho Cp to DAB, and temperature by rho. I do not expect, I do not want you to solve this in your examination. Right up to this part, then in the next step directly write the solution from your textbook. Identify the problem, find out the solution for heat transfer, mass transfer, momentum transfer anywhere from any book, any mathematics, write the solution. Okay? Do not have to go through any steps. So, the solution for that is going to be if this is a heat transfer problem, this would be theta, this would be the that theta constant theta that you are using at x equal to 0. Instead of DAB, you are going to write alpha, that is it, no change. When you see your class notes now, you would see this is going to be equal to your theta, and this is the theta whatever constant, this would be alpha, that is it, no other changes. So, if you know that part, you know this part as well. Okay. So, this is my concentration profile inside the liquid. Now, what I am going to do is I am going to take this salt layer and find out the write the conservation equation. So, in minus out plus accumulation is in let us say in minus out, there is no accumulation term. So, in minus out is whatever you have rate of change of storage of the thing. What is the in term of this salt? Is there any salt you are adding to this control volume? No. So, this is 0. What is the out term? The dissolution that you are going to have in water. And what is the stored term? Obviously, the length or thickness, whatever you call, the thickness of this is changing. So, if your cross sectional area of this is A, then the rate of change of stored term is simply going to be d dt L A multiplied by rho of the salt. And which rho I am going to use here? 2165 or something, rho of the salt, solid salt, because I am writing it for the solid. And what is going to be my out term? It is going to be whatever mass flux I am having here at the surface, that means this is evaluated at x equal to 0 multiplied by area. Are we sure what we are doing here? Out term at this control surface is will be equal to the rate at which it is getting solubilized in water. What is the rate at which it is solubilizing in water? I know what is the concentration profile. If I know the concentration profile from here, I should be able to find out what is the mass flux, right, because mass flux is nothing but dAB multiplied by del C A del x evaluated at x equal to 0. My NaX is nothing, my NaS is nothing but this one. Are we comfortable? Should I repeat it? Do you want me to repeat it, or you understand it now? So, the mass flux or dissolution rate is simply equal to dAB times del C A del x evaluated at x equal to 0. This is going to be equal to d dt of rho times L, where rho is a constant. So, rho can be taken outside. So, it is simply going to be rho times dL dt. I am writing the conservation equation, and this conservation equation I am writing for mass. So, that is why I am using mass flux. There is no question of writing molar flux here, it is a single component system. Okay. Okay, del rho A by del x, fine, agreed. So, is that clear? The flux, the mass flux multiplied by the area is the dissolution rate, kg of salt being dissolved in water, and on the right, the dissolution rate is connected by a mass balance with dL dt. So, you already have the expression for rho. You should be able to find out what is del rho A del x evaluated at x equal to 0, and this would give you dL dt. The only mathematical thing that you are going to use is you have to find out d dx of that at x equal to 0. Have you done that before? Okay. It is just again use it as a tool. I will give you this d dx of error function x by 2 dAB t to the power half evaluated at x equal to 0. This is what you have to do, is simply equal to 1 by pi dAB t to the power half. All right. So, this is what you are going to get. This is a standard formula which you can definitely use without any problem. And the best is, if I call this A, it would simply be equal to pi A to the power half. So, you can use it for heat transfer, mass transfer, does not really matter. So, once this is known, you should be able to find out what is dL dt. And once the second part of the question is how much the salt layer, top layer would recede in 24 hours. If you have dL dt, you should be able to integrate it over time and find out. This answer is 2.02 millimeter. So, delta L over a 24-hour period is equal to 2.02 millimeter. So, conceptually there is nothing except realizing the fact, realizing the proper form of the governing equation and making a mass balance at the interface. Okay. Thank you.